Let's look at how the entropy changes when we change the temperature of the system. We can imagine doing this in two different ways. We can use a constant pressure, in which case when we input energy as heat to the system, the volume will increase and we will do work on the surroundings. On the other hand, we could increase the temperature at constant volume, in which case when we input energy as heat from the surroundings to change the temperature of the system, the final pressure will be greater than the initial pressure because the volume has stayed the same, and we will not do any work on the surroundings. In both cases, we have input energy as heat from the surroundings, and so as energy enters the system as heat, energy must be lost from the surroundings as heat. Thus, as we have discussed previously, the entropy of the system will increase due to the increase in temperature. The entropy of the surroundings, however, will decrease because we're losing heat from the surroundings. In general, the reservoir has far more particles and is a much larger system, and therefore has way more microstates available to it. The system has a far fewer number of particles, is a much smaller system, and therefore has less microstates available to it. If we start initially with the temperature of the system being at a relatively low temperature, and the temperature of the reservoir or the surroundings being at a relatively high temperature, then the surroundings or the reservoir will have far more microstates available to it than the system. So if we look at how the number of microstates changes as the process occurs, the system will start with a small number of microstates, and as the system's temperature increases, the number of microstates will increase. On the other hand, the surroundings starts with a large number of microstates at a higher temperature, and as its temperature decreases, the number of microstates will decrease. Because the system plus surroundings are adiabatic, we can apply the second law to the system plus surroundings. The number of microstates of the total system, system plus surroundings, is the product of the two numbers of microstates. And so we can see that there will be a maximum at some point in the number of microstates available to the system plus surroundings. The second law tells us that the system will be in equilibrium when the number of microstates is no longer changing. That means that the slope of the number of microstates in time is equal to 0, and that occurs at the maximum. And so we will be at equilibrium when we are at the maximum number of microstates. Thus, we can say that the system plus surroundings will maximize the number of microstates available to them. This maximum in the number of microstates always occurs when the temperature of the system is equal to the temperature of the surroundings. Furthermore, because the second law tells us that the spontaneous direction is the direction in which the entropy increases, or ds is greater than 0, the slope of the microstates with time must be greater than 0 for the spontaneous direction. And therefore, we will always go in a direction, the process will occur in the direction where the slope of the number of microstates with time is positive. This means that the hot temperature will always lose microstates, and the colder temperature system will always gain microstates, and thus heat always flows from the hotter body to the colder body. In the two examples shown here, the reservoir is a higher temperature than the system, and so heat is flowing from the reservoir to the system and increasing the temperature of the system. If we now want to calculate the change in entropy as we change the temperature of the system, in this case at constant pressure, we need the partial derivative of s with respect to t at constant p. The second law tells us that ds is equal to dq reversible over t, and therefore the partial derivative of s with respect to t at constant p is equal to 1 over t times the partial derivative of q with respect to t at constant p. But the derivative of q with respect to t at constant p is our definition of the constant pressure heat capacity, and so ds dt is equal to c sub p over t. Now that I have an expression for my partial derivative that I want to calculate that is in terms of measurable quantities, I simply need to separate variables. ds equals c sub p dt over t, and then integrate. So I'm going to integrate from my initial state to my final state. And in my initial state, my temperature is T initial. In my final state, my temperature is T final, C sub P dt over T. And when I do that integral, I get that delta S for the constant pressure case is equal to C sub P natural log of T final divided by T initial. In this case, I've assumed that the heat capacity does not depend on the temperature because I've removed it from the integral as a constant. I can make the same argument for the constant volume case and show that delta S for the constant volume case is equal to C sub V natural log of T final over T initial. Now, since the heat capacity at constant pressure is greater than the heat capacity at constant volume for most substances, we can see that the change in entropy for the constant pressure case is going to be larger than the change in entropy for the constant volume case. This makes sense because in the constant pressure case, not only am I increasing the temperature, I'm also increasing the volume, both of which increase the number of microstates available to the system, and therefore both contribute to an increase in entropy. In the constant volume case, I can't do any work, the volume doesn't change, and so it's only the increase in temperature that increases the number of microstates in the system, leading to a smaller increase in entropy in the constant volume case.